Hello, I'm Guang Hong from Purdue University. I'm going to talk about our work, Backdoor Trigger Inversion Optimization in Backdoor Scanning. This is a joint work from Purdue University and Rutgers University. Backdoor attacks are prominent threats to deep learning models. An attacker can inject a small backdoor trigger on the image and use this to train a new model. This new model will misclassify any inputs with the trigger to the target label fish. Backdoors also exist in naturally trained models. For example, for a benign model downloaded from Chaos Model Zoo, an attacker can also generate a trigger for turtle images, which is called a natural backdoor. If we add this trigger on any turtle images and feed them to this benign model, it will misclassify them to kangaroo with high confidence. Backdoor scanning is an active area aiming to identify these backdoors. Trigger inversion is a widely used technique in this area. It leverages optimization to drive a small input pattern. This inverted pattern can flip a set of clean samples from a victim class to a target class. For injected backdoor, trigger inversion is commonly adopted in scanners to decide whether a model is backdoored or not. That is, the scanners leverages trigger inversion to generate backdoors for each target class and aim to see whether an exceptionally small trigger can be found. For natural backdoor, trigger inversion is used to directly generate small triggers that can cause high attack success rate on benign models. The size and ASR are important factors to a good trigger inversion technique. Now let's see what the inverted triggers look like by an existing method and ours. Suppose we want to generate a backdoor from turtle to kangaroo. This is the trigger generated by the baseline. You can see a lot of pixels are perturbed, and the ASR is only 28%. Here is our generated trigger. Ours has a much smaller number of perturbed pixels, and the ASR is much higher. Since our trigger has a different number of perturbed pixels, we hence remove unimportant pixels in the baseline trigger. You can see the ASR drops to 22%, meaning the removed unimportant pixels still contribute to the ASR. Besides, it takes 9 minutes to generate a trigger for the baseline and only 4 minutes for ours. Here, we study why the baseline is less effective. This figure shows the loss surface of the baseline. The x-axis and the y-axis denote two random directions, with x equal to 0 and y equal to 0 the optimum. The z-axis shows the loss value. You can see there are multiple dips on the loss surface, which means the baseline can easily stuck in some local minimum and fails to reach the optimum. This figure shows the loss landscape of our method. You can see our loss surface is much smoother. The loss values all descend along the valley towards the optimum point at the bottom. This demonstrates that our method is able to easily find an optimal small trigger with high ASR. We conduct experiments to generate natural backdoors on ImageNet models. The results show our trigger inversion method is 2 orders of magnitude smaller than the baseline, has 20% higher ASR, and 2 times faster. For backdoor scanning, we replace the trigger inversion method in existing backdoor scanners with ours and apply them to detect points in the models. For 3 advanced backdoor attacks, the scanners with our method can successfully detect them, whereas the baseline cannot. The scanner equipped with our trigger inversion method also outperforms the state-of-the-art backdoor scanner on 300 pre-trained models. Please come and visit our poster 7B. I'm happy to take any questions.